Well, this is the last technical session. It's going to be the best, right? I checked with the president of the US and he says it's absolutely perfect. And we have 3 papers on disparate topics in ICN architecture. So we have a pretty broad brush here. So we have one on DDoS mitigation involving how to damp interest flooding attacks. We have a paper on how one might tightly integrate coding into an ICN architecture rather than treating it as an add-on, as many of the current approaches do. And a paper on how to design an ICN end-to-end transport that's somewhat independent of the underlay network that it's running on. So diving right in, our first paper is entitled Persia, a puzzle-based interest flooding attack countermeasure. And it's authored by Reza Tourani from St. Louis University, George Torres from New Mexico State University, and Jay Misra, also from New Mexico State University. So the paper is going to be presented by Reza Tourani, who's an assistant professor in computer science at St. Louis. He got his PhD from New Mexico State in 2018. Research areas in security, privacy, future internet architecture, smart grid, cyber physical systems, and has had quite a few peer-reviewed papers in ACM journals and conference proceedings. So please load up the video for our first paper.
My name is Reza Tourani. I'm assistant professor at St. Louis University. Today, it's my pleasure to present Persia, a puzzle-based interest flooding attack countermeasure. This is a joint work with Jay Misra and George Torres at New Mexico State University. In the past few years, we have been observing a sharp increase in the number of distributed denial of service attacks on the internet. We just compared the number of attacks in the first quarter of 2015 and 2018. We can see that the number of attacks, the frequency increased from about 200 to 1,500 attacks. This is in part due to the infusion of smart devices to the edge of the network, which usually enter the market without proper security onboarded to the network with weak security, and also the popularity of the memcached services. If you look at the past few DDoS attacks, you can see the footprint of these 2 events. In particular, the DDoS attack on DY and DNS in 2016 was from Mirai botnet that is comprised of like 600,000 compromised IoT devices with a peak strength of 1.2 terabit per second. In 2018, GitHub reported an attack with a peak strength of 1.3 terabit per second. And just earlier this year, Amazon reported an attack with a peak strength of 2.3 terabit per second. Now we can see that not only the frequency of the attack is increasing, but also the strength of the attack is on rise. The interesting fact about the 2018 DDoS attack on GitHub was it didn't last more than half an hour, and the reason was GitHub was using Akamai scrubbing service. Scrubbing service is one of the most common DDoS mitigation in IP network. The way it works is the victim requests a service from the provider, from the service provider. The service provider, in the case of GitHub attack, was Akamai. They redirect the traffic from the malicious and legitimate user toward the cloud, toward the scrubbing center they own. And then this happened through DNS or BGP. In the scrubbing center in the cloud, the service basically separated the malicious traffic from the legitimate traffic by looking into the packet attributes and traffic attributes. Something like the destination and source IP address and port number, TCP flags, and HTTP traffic characteristics. And then forward the legitimate traffic towards the provider so it can serve the client. Looking at this type of solution, we can easily see that we cannot apply these solutions to NDN networks. One of the major reasons in NDN, we don't have any distinction between malicious packet and legitimate packet. There is no notion of client there. That actually motivated us to look into different distributed denial of service attack in NDN and try to come up with a solution that can resolve the problem. Now, before talking about the solution, let's look at the 2 types of DDoS attack in NDN. The first, that is called IFA, is interest flooding attack. The goal of attackers is to overwhelm the network resources in particular, the PIT of the intermediate router through sending volumetric malicious traffic. In contrast to IFA, which is using volumetric malicious traffic, implicit denial of service attack, or IDOS, attackers are basically trying to craft multicast requests with the particular timing and using the features of NDN like request aggregation and loop prevention features to prevent the victim's attack to the requested content. Now, we looked at the existing literature in IFA mitigation, and we noticed that rate limiting is one of the most popular mitigation technique in the literature. The way that rate limiting works is each router individually or collaboratively, they monitor the rate and the statistics of interfaces to detect an attack. When an attack is detected, they basically rate limit that interface. Another interesting solution was self-routing, that is essentially removing the suspicious interest from the PIT entry and then add routing features to the name of the packet. We can see the example of this at the bottom of the figure. However, these techniques actually show some shortcoming. In particular, for the case of rate limiting, we noticed that rate limiting can negatively impact the quality of experience of the users that are co-located with malicious user. And again, the reason is in the end, there is no notion of client inside the request packet. So it's really hard to differentiate which packet is coming from the malicious user or it's coming from the legitimate user. As for self-routing, self-routing actually changed the name of the request as it goes toward the network, which means it undermines caching and request aggregation. Also, it contradicts the NDN's content name immutability. So this actually motivated us to look into IFA problem, and then we actually come up with the idea of Persia, which is an ISP-based countermeasure that employs the independent prevention and mitigation mechanism. So Persia can be deployed in an ISP at the core and at the edge of the network. At the edge of the network, the prevention phase can be deployed. The essential idea behind the prevention phase is pushing user to use tokens in their communication. And then the idea of the mitigation phase that will be deployed on the core of the network is try to remove the suspicious interest from the P table and store them in other type of structures, in particular in Bloom filter. Now let's look at the prevention phase a little bit more closely. In the prevention phase, the client has to obtain some computational puzzle from the proxies, solve this puzzle, generate a set of tokens, and then use these tokens for communication. In Persia, we actually use Lagrangian polynomial interpolation as the computational puzzle. However, I have to say that other type of computational puzzle, something like cuckoo cycle, the hash chain, or even Bitcoin hash cache or Diffie-Hellman puzzle can be used. It's essentially a plug and play feature that can be replaced with any type of computational puzzle. Now, when the user solves this puzzle and generate the solution, they can essentially use that solution to generate a sequence of tokens and use each token only once in their communication. The way it works is the client has to go to a proxy that is deployed by the ISP, request a puzzle, and obtain it either from the proxy or a cache puzzle from the edge router. Having the puzzle in hand, the user needs to solve the puzzle, generate the solution. Each puzzle is also associated with a secret seed that together, hashing the solution and the secret seed together can generate the very first token in the token chain of the client. Having the first token, the user can go through a sequence of hashing operation, hashing the token, the previous token, and the secret seed, and generate a set of K tokens. Now with this token, user is ready to do the communication. However, for the edge router to be able to validate this token, it needs to build the verification table. So the edge router needs to get in touch with the proxy and its users. So by receiving those information, including the puzzle name, the puzzle solution, the secret seed of the puzzle, the very first token, and the limit of the token that can be associated with that puzzle, the edge router can create this table. Now, having this table, when an edge router receives a request and interest from the user, it simply can verify the token by looking up the token in its table. If the token doesn't exist, the edge router simply rejects the request and drop the communication. However, if the token is available inside the verification table, the router forwards the packet or does the cache lookup and then update the verification token. The process of updating verification token is fairly simple. The edge router needs to just generate the next token, which is simply one hash operation, and updating the counter to make sure that the user is not overusing tokens. Now, this actually concludes the prevention phase of Persia. However, we noticed that there are some edge router that might not deploy this process. Or if you have a compromised router that does not perform the verification, it actually can forward all the requests, malicious and legitimate, toward the core of the network. And that actually ends up being the major problem in a lot of existing solutions. Now, for that reason, we design a forwarding strategy and mitigation strategy that we call it Bloom Filter Assist Mitigation Strategy, BFA, that the core router can independently run it on their own. Now, this phase actually helps the core router to mitigate the impact of compromised edge routers. The way it works is each core router individually and independently monitor all the interfaces, collect a statistic, in particular the loss rate of that interface. As soon as the loss rate goes beyond a certain threshold, the attack is detected. When the core router detects an attack on a particular interface, it actually detaches the request that arrives from that suspicious interface from the PIT, and then associate a counting Bloom filter to that interface. Using this counting Bloom filter, every time the core router receives an interest from that interface, it adds the name of the request to this counting Bloom filter, and then process the interest. By processing the interest, I mean that it can perform an aggregation or forward the packet toward the core of the network. So using individual counting Bloom filter for suspicious interfaces allows Persia to do request aggregation, even if you have malicious interest or interest coming from malicious interfaces. So the aggregation can happen either through the PIT, which is the normal NFD operation, or if one of the interfaces that is using counting Bloom filter has the requested content name inside the Bloom filter, then the core router just add the name into the other interface and then aggregate the packet, doesn't forward the request toward the core of the network. This example shows that in the very first step, the router that is connected through the core router on interface 2 sends a request. This request will be forwarded to the core, but when the other router sends the same request over phase 2, the core router look up the counting Bloom filter of phase 2. It sees that that data has been requested before, so it simply add the request name to the counting Bloom filter of interface 1 and aggregate it right there and won't forward it to the core of the network. Now, through this mechanism, whenever a core router receives a data packet, it needs to perform a PIT lookup to answer the request that has been aggregated in the PIT through the interfaces that are performing normally. And then it iterates through all the interfaces, suspicious interfaces that are using counting Bloom filter, and look up the name of the packet in the Bloom filter. If a hit happens, the core router forward the packet through that interface and then remove that packet name from the counting Bloom filter. So to estimate the efficiency and the strengths of our proposal, we actually model different types of attackers, including the attackers that requesting data without solving puzzle or invalid token, attackers that are hijacking user token or performing replay attack, the user that shared their token or their solution or credentials to the other attackers, and then more importantly, the compromised infrastructure that is missing from most of the existing literature. In the paper, we talk about all of these attacks and how does Persia solve these attacks. We also talk about two other types of attack: the puzzle complexity and solvability in case that the attacker hire a botnet, and attacks on proxies, the proxy that generate the puzzles. However, in our simulation, we actually group these attacks together. So group one include the attackers that they don't use token or use fake token. The second group is about the attackers that share their information with the others, token hijacking and replay attack. And the third group is basically the compromised infrastructure. Now, for our simulation, we actually used 3 rocket fuel topology, Bond, Lestra, and AT&T. And you can see the specification here. As for the edge router, the red number in that row shows the number of compromised edge router that we add to our simulation, which is roughly 25% of all the edge routers in particular topology. We also add 10 provider and 5 proxy to all the topology that we have and made sure that the number of attackers is roughly equal to the number of legitimate user. As for the user, the request rate is selected uniformly at random from the range between 20 to 30 packets per second. Following the ZPF distribution, the client requests data. For the attacker, we actually use CBR attacker, and the rate of the attacker is selected uniformly at random from the range 50 to 100. And we made sure that the attacker are not requesting repetitive data. So each attacker requests individual data and never requests a data twice, just to make sure that there is no aggregation among the attack traffic. So it's actually making sure we have a full-blown attack. We ran the simulation for about 2,500 seconds and averaged the result over 5 rounds. One of the problems is we cannot mimic the computational operation in LDN SIM. So actually we benchmark the puzzle solving time and the size, and we infuse it to our simulation. So we selected the puzzle difficulty of 5K, which is the difficulty or the degree of polynomial is 5,000. We benchmark this operation and then apply the corresponding latency whenever the user has to solve the puzzle. One thing that we did is we compared the result of BFA with self-routing and rate limiting. So all of these 3 strategies, they use Persia's prevention phase, but when we introduce the malicious routers, they use different type of a strategy. As we can see, the first 500 seconds of the simulation is our baseline, which means we don't have any attacker. 500 to 1,000, we have attacker A1 and A2. 1,000 to 1,500, we introduce attacker A3. And between 1,500 and 2,000, we introduce all the attacker together for a full-blown attack. And at the end, the last 500 seconds, again, we stop all the attack to see the recovery. As we can see here, this is basically the latency experience of the client. We can see in SR Plus and BFA, the user don't experience any latency degradation even during the attack. However, in RL, the story is different. As soon as we introduce the compromised edge router that let all the malicious traffic into the network, the rate limiting basically start dropping the packet from even legitimate user and then cause retransmission, which result in higher latency for the client, so lower quality of experience. And this is also backed with the satisfaction rate that we observed for RL strategy. We can see the satisfaction rate of the client for RL is something between 75% to 80%, 85%. However, SR Plus, which is self-routing, an update of self-routing, and BFA, which is our proposal, they could achieve almost 100% satisfaction rate. The small value of the drop in SR Plus and BFA is just because of the false positive of the Bloom filters. Looking into the throughput measurement of different entities, including users, edge router, and core router, we can see in rate limiting, as soon as we introduce the compromised infrastructure, the expected throughput reduces a bit for all the entities, user, edge router, and core router. This is expected because now we have packet drops and the user have to do retransmission, and the network is observing a lot of packet drops. In SR Plus, interestingly, the throughput for the core router increased. And this is an undesired property. The reason is it's not the higher throughput. It essentially means that SR Plus cannot do the request aggregation. It sends all the traffic to the core of the network, even all the legitimate traffic to the core of the network, and then it overwhelms the resources in the network core. However, BFA shows that regardless of the type of attack that we are introducing at different time in our simulation, the throughput measurement of all the entities is always steady. It shows the strengths of BFA and the little impact it might have on the core of the network. We also look into the overhead to back up our hypothesis about SR+. Now here we can see the overhead of the communication among the three strategies. The orange color is showing the overhead of SR, self-routing. The blue line is showing the overhead of rate limiting, and the gray one is the BFA. Something that we can observe is SR+, because of lack of aggregation, is showing the highest communication overhead. And this overhead actually increases with the size of the network. If we compare IBON with AT&T, we can see that the overhead increases dramatically. Following that, we can see that rate limiting has overhead smaller than SR, but is still bigger than BFA. And BFA is always the least overhead on the network, which sort of proves that it can satisfy the quality of experience of the user, but with minimum overhead and minimum pressure on the core of the network. Now we have more results, but to the interest of time, I don't present it here. I'll join the meeting after the video and answer all the questions. So just to recap, we proposed Persia, which is proposing an edge-centric DDoS prevention mechanism that is deploying at the edge of the network, and a dynamic network mitigation strategy that can be deployed on each core router. So each core router can individually and independently decide to deploy it or not. So the objective of Persia was satisfying the expected quality of experience of the user, which through the simulation showed that it can achieve that type of quality of experience, also imposing minimal impact on the network resources, which shows through the simulation, we showed that the communication overhead of Persia is much lower than self-routing and rate limiting. As part of our future work, we're actually trying to integrate Persia with the token-based access control. And the reason is we're trying to get rid of the proof of work part and allocate the token that are basically reuse the token that are used for the access control as part of DDoS mitigation, which make it more desirable solution. With that, I stop here and we'll join later to take any question you might have. Thank you.
Hi, so we have sort of a couple of discussions going on in the Slack. One of them is related to whether large-scale IoT systems where the devices themselves have low computational power might not be able to solve a complicated enough puzzle or solve a puzzle fast enough that you can use this scheme, in which case they can flood an IFA attack. Do you have anything more to say about that besides what's posted in the Slack that people can look at?
Basically the answer is that one. The answer is we can dynamically adjust the rate or the difficulty of the puzzle, especially if the network is under attack, and considering majority of the DDoS attack coming from IoT devices, it makes sense to slow those devices down. There are also other cases that basically people talking about IoT devices are part of botnets without even their owner knowing about, and that's contributing to DDoS attack. And basically they might not solve the puzzle, send the request, or even there is no problem. They take long to solve the puzzle and then launch the attack after that. But that's the mitigation phase of Persia that kick in and try to prevent even the attacker that trying to solve the puzzle and then overload the network.
So I had a sort of related question, which is when I looked at the protocol machinery, it seemed like this could in fact be done by the first router at the edge of the trust boundary rather than the device itself because of the symmetry of the protocols. Is that true? In other words, could your first hop router, which is essentially on your side, you know, not on the network side of the trust boundary, but your side of the trust boundary, solve the puzzle and interact on behalf of a set of IoT devices? So the key thing is that the puzzle has to be solved outside of the trust boundary and verified inside the trust boundary. Is that the right understanding?
Correct. You're absolutely right, Dave. That's actually a nice way of doing that, especially considering for a lot of IoT devices, they're sitting behind an edge server or a router, and then that operation can be delegated to the router or the server. Okay,
and there's another question about how you prevent attackers from generating valid tokens. So could you quickly sort of go through that again?
Right. For generating a valid token, first a puzzle should be solved, and that's the computational part of the work. And then after that, a sequence of token can be generated. For generating those sequence of token, user need to have that secret seed. Without that one, no one can generate the next available token. So it's basically a way, and each token when it's generated is part of a sequence, and it's basically allocated to one individual user.
Right, and there's a question from Mike Luby about whether you think the amount of computation being done is enough of a load on battery life to worry about.
Right. Actually, your suggestion there was a good answer, because this operation can be delegated to the server that's allocated for the IoT devices. And another thing I mentioned at the end, the second approach is basically we're trying to look into this edge-based access control mechanism in ICN and trying to reuse the token that are for access control for DDoS mitigation as well.
Okay, thank you, Reza. Any other questions that I haven't seen in the Slack that some people would like to ask online, or should we move on? Okay, so let's move on to our second paper of the day, whose title is Liquid Data Networking. Very inventive title, I would say. We'll hope that the presentation will elucidate what's, how that title can be really interesting. The paper's by John Byers at the Computer Science Department of Boston University, and Michael Luby, who's with ICSI and BitRipple in Berkeley. Mike will be presenting the paper. He's probably well known to quite a subset of this community, although some of the pure ICN folks may not have come across his decades of work in math and coding theory. But he earned a bachelor's PhD in theoretical computer science at Berkeley, was the co-founder of Digital Fountain, one of the early coding companies, and pioneered fountain codes, which have been very popular over the years, and has achieved, renowned in the industry on a number of areas, and is a recipient of quite a few awards. I don't really feel like going through them. You can look them up on the web. He's also a member of the National Academy of Engineering and an IEEE fellow and an ACM fellow. So we have the distinct privilege of hearing a luminary of the field to give this paper. So let's cue up the video, and Mike is online.
Hi, I'm Mike, and today I'm going to be talking about liquid data networking. This is joint work with John Byers. Our work is concentrated on integrating erasure codes into ICN. Erasure code benefits include resilience to packet loss, reduced latency via downloads over multiple interfaces, improved support for mobile clients, improved caching performance. Potential integration overheads include signaling, latency, security, response, and storage. Previous work does not extract the full benefits. Each has issues with at least some of these overheads. Our approach is a network architecture design that provides benefits and minimizes overheads, and also provides a seamless integration into NDN. The LDN focus within ICN is on object to network data name mapping, where an object is a unit of data that is useful. A packet is a unit of data that is transported or cached in the network. And mapping is from object name to packet name. Request response paradigm is how clients and nodes request packets for an object and how nodes respond to requests with packets. Security considerations include an end-to-end object verification and packet verification to prevent denial service attacks. The NDN approach to these things is you have an object that has a name D. It's partitioned into source packets, and those are given names derived from D, for example, D.0, D.1, and so on. The request response paradigm is that the client explicitly requests all the source packets by name for the object. Security is provided by publishers signing packets and nodes and clients validating signed packets. Clients accept an object if all of its source packets are valid. There's been a lot of good work on integrating erasure codes in ICN. Some of it's shown on this slide here. Of course, there's a lot of other work as well. On the top is shown an object, which is partitioned into K source packets. An erasure code is used to generate additional repair packets, where capital N is the total number of available packets for this object. Coordination strategies are important. An additive response strategy is where the same client receives different packets from different nodes. So as shown on the bottom left, the client is downloading an object from two nodes concurrently, and it's getting purple data from the left node and green data from the right node. And this is important to minimize response overheads because it wants to recreate the object from the minimal amount of data possible. Common response is also very important. This is when different clients receive the same packets from the same node. So for example, on the bottom right, the node is supplying the same green packets to both clients for the same object. And this is important for caching efficiency. And it's also important for signaling and response efficiency, as it sends the request up the stack just once and receives one response back to this node before it provides the responses back to the clients. Prior request strategies include asking for specific data, where a client asks for specific packets of data by name. This is, for example, what NDN does. This does have an issue when a client is asking for packets over multiple interfaces from different nodes. The question is how do you enable a common response? Random data is a very popular strategy that's used by erasure code approaches. This is when a client requests an amount of data packets and the response is randomly generated encoding data. How to distinguish between common and additive response is a difficult issue here. So in some cases you want to give a common response and an added response. Further details are discussed in our paper. Useful data is when a client specifies data it has already received and the response is additional data that will be useful. This, as others have pointed out, has an issue with additive response and also has some signaling overheads. LDN enables coordination through the introduction of the key concept of a Soapy, where Soapy stands for Stream Object Permutation Identifier. A Soapy P defines a permutation of all the available packets for an object. So as shown below, there's an object D that consists in size of 5 source packets. And for this object, there's n equals 11 packets in total available, and those are shown in a canonical order, ordered 0 through 10. And then in this example, the Soapy P equals 3,5 identifies a new ordering of these packets, where the new ordering is 3, 3 plus 5 is 8, 5 plus 8 is 2 mod 11, and so on. And this is the ordering of the data in the object, stream object D.P. The LDN request response paradigm is that a Soapy is assigned to each node and a client requests prefix of stream object associated with the Soapy. So in particular, in the example below, the client on the left is trying to download a data object D, and it asks for a prefix of the stream object D.P0 from the node on the left that has Soapy P0, and a prefix of the stream object D.P1 from the node on the right that has Soapy P1. And if these prefixes are non-overlapping, then this provides the additive response capability. And then the common response is shown on the right, the node on the right on the bottom where it has assigned Soapy P1. And both clients are asking for a prefix of the stream object D.P1, and it provides the same response to both. LDN desirable properties are to support large K. Small k forces splintering of objects into many source blocks, which causes large response overheads, which is to be avoided. Support for n bigger than k, in particular n bigger than k squared, is a good choice. This allows minimal prefix overlap of stream objects with different Soapies. In fact, it can be shown that if you choose the Soapies randomly, then with very high probability, they will have a very small overlap for the condition above when n is bigger than k squared. And in going further, you can design a large set of Soapies deterministically that have guaranteed small overlap between their prefixes. And both of these are shown in the reference that's shown on the bottom of this slide. Some erasure code properties that are desirable are linear coding complexity, especially when they're coding repair packets only, because when n is bigger than k, a lot of the packets you're going to be dealing with are repair packets. Erasure code choices include random linear network codes and Reed-Solomon codes. They have significant complexity response overhead trade-offs. The fountain code has okay trade-offs, and the Raptor Q fountain code has near optimal trade-offs. More details can be found in our paper. Here's an example of a network we call the Turkey network, where there's two clients on the bottom, both trying to download the same object D concurrently, each from two nodes. And so these are the requests that are going up. As those requests percolate up towards the publisher, the node in the middle with Soapy P1 coalesced its request into a single request for the prefix of the stream object D.P1. And then as they go up, the node just below the publisher node has shortened its request. Instead of asking for k/2 from each stream object, it only asks for k/3 because it knows as soon as it gets k back, it can recreate the object and provide the remainder of the responses on its own without any further communication with the publisher. And so what happens is the publisher provides the responses, it lets those go down to the clients, and then as soon as it has k, recreates the object and generates the rest of the responses and provides those down the stack. So at the end of the day, it looks like this, where the clients at the bottom have enough packets to recover the original object, D, and the middle nodes each have k/2 packets cache for D that they can use to provide responses to future client requests. Here's another example of load balancing where the nodes each have an assigned Soapy and the clients are provided all those Soapies. So each client requests an equal fraction of the packets it needs to regenerate the object from each of the nodes. So in this example, k/5 from each. And so what this does is it provides automatic load balancing. The requests are equally spread across the nodes in the middle, and also saves a factor of 5 on storage overhead versus conventional load balancing. This is easy to maintain and transparent to end users. LDN security, we think it's important to distinguish between originator and publisher, where originator is the original generator of an object. It's preferable if this entity is network independent. And a publisher is where the object is available in the network. For example, it's the node where the object is injected into the network originally, or the node that generates the object from packets received as the protocols go forward. Object verification is straightforward. Originators sign objects using standard digital signatures. Clients verify objects, and this ensures end-to-end integrity. Packet verification is only slightly more complicated. Publishers verify objects before they generate any packets from them because they want to make sure they're okay. And then publishers, as they generate packets, they sign those packets together with the object credentials. And nodes and clients verify the packets. With this, the misbehaving publishers can be identified and blackballed. In summary, clients are in control. Clients make explicit requests, avoid response overheads. Choosing and assigning Soapies is an interesting problem. Different Soapies are assigned to nodes from which the same client downloads is an important design principle. Seems like a small number of Soapies overall may be possible, TBD. Security, it's important, we think, to make the distinction between originator and publisher. And finally, LDN is an architectural extension of NDN where the same interest message response protocols can be the same as in NDN. The NDN naming and other features can be directly leveraged, and the benefits of erasure codes achieved and overheads avoided. Thank you.
Okay, so I haven't seen any questions on the Slack, some nice interpersonal conversation. I'll ask one question where the motivation here is that n can be very large compared with k, potentially k squared. What do you think about the time-space trade-offs with having such large n? And does the originator have to generate all n packets beforehand, or can it be done on demand when Soapy requests get there so that you actually don't have to pre-store this quadratic expansion of storage?
So great question. There's no, I guess one of the very important points of this whole thing is that never do you ever create these n squared packets. Everything is on demand. So when you are asking for a prefix of a stream object, you're generating those as you ask for it, and you only generate the ones you actually ask for. So the amount of data you actually ever generate for this object is a small fraction of the object size from any particular source. That makes sense?
Yeah, it makes perfect sense, but a quick follow-up. So one of the properties that people have touted for NDN is that because of the extensive opportunistic caching, it's possible to survive publisher outages that are relatively long.
Right.
In which case, if you wanted to do that, and the publisher, in fact, is the one who's generating all of the coded packets, you would, in fact, have to generate all of them in advance, right?
No, so what happens is where you inject it into the original publisher obviously has everything, right? And then as the packets flow through the system, if enough packets flow through some other node, they can automatically become a publisher for this object as well. And in fact, we should have.
If they hold the whole object.
If they take enough packets to be able to recreate the object, yes.
Create the whole object, right?
Yeah, yeah.
So that might affect your caching policies, but it certainly might. Yeah, it certainly allows you to achieve the resilience.
Yeah, exactly. The other thing that we didn't talk about in the talk, but there's some other approaches that use blind encoding, which they sort of recode based on partially based packets that they've received. They can't recover the whole object, but they start coding on packets they've already received from other ones. And that has some serious security concerns, as we point out in the paper.
Right, yeah, network codes could do that, but you have interesting security problems. So there's another question on the Slack from Jay Misra, which is commenting on whether can be done with the client not knowing where to go to get which set of blocks.
Yeah, the client doesn't really need to know much, right? All it needs to know is the SOAPs of the edge guys near it, right? So all it does is send out these requests for the object together with the SOAPy attached to it. So it doesn't really need to know where the publisher is, or where the data is generated is far away from the client, at least in the beginning. It's some publisher way up at the high end of the network. But nevertheless, it can get locally the information and say, hey, from this guy, I'm going to add for this prefix stream object prefix, and from this other guy, this other stream object prefix that are going to be non-overlapping. But where those codes get generated can be far away from where they're requested. So the client doesn't have to have any global information.
Good. So Ken has a question saying, figuring out how to choose the place where you forward your request to is, can that be mapped into what NDN calls a forwarding strategy?
Yeah, no, so there's a lot of open work, and he's picked up on one of them for sure. Right? Where do you put your SOAPs, and where do the clients get them from, and so on. That's really interesting work that we obviously didn't have time to even touch on in this short presentation, but even in our fuller work, there still needs to be a lot of work being done there.
Super. Anything else from anybody before I close it out? No. So thank you very much, Mike.
Sure. Thank you.
And we'll move on to the last paper of the session. We're getting down to the nitty-gritty here. So our third paper is called Named Data Transport, an End-to-End Approach for an Information-Centric IP Internet. The authors are Aziz Albalawi and JJ Garcia-Luna-Aceves, both from the CS department at UC Santa Cruz. The paper will be presented by Aziz, who's a PhD candidate at UC Santa Cruz, advised by JJ, and a member of the Computer Communication Research Group there. He's currently working at Fahad bin Sultan University in Tabuk in Saudi Arabia as an instructor in the computer engineering department. So I don't know whether he's joined from Saudi Arabia, but let's hope the network holds up if that's the case. So let's start the video, please.
Hello everyone, my name is Abdulazaz Al-Hamoudi. I'm a PhD candidate in the Computer Engineering Department at the University of California, Santa Cruz. Today, I'm going to be presenting named data transport, which is designed to provide efficient content delivery by name over the existing IP internet. This is joint work with my co-author, Professor J.G. Garcia at the Computer Communication Research Group at UC Santa Cruz. So the original use of the internet was to share expensive limited resources such as printers by addressing endpoint using IP addresses. However, the current internet usage today has been shifted toward accessing content such as video with platforms like Hulu, Netflix, or Facebook rather than to share resources. This can be seen from the right figure, which shows the high anticipated increase in the video traffic in the future. Also, mobility was not a concern back then. However, a big portion of today's traffic and in the future will be carried over mobile devices. And that's not just with cell phones, but with the breakthrough of Internet of Things, like in smart cities and Industry 4.0. In addition, the current internet leaves security to the end host. So all this results in many drawbacks when dealing with large data distribution, privacy, and mobility. The limitation of the Internet model to provide reliable and efficient access to contents and services led to the development of dedicated solutions aimed at content delivery. These systems can be categorized as content delivery networks like Akami or peer-to-peer applications like BitTorrent. While such content delivery systems address many of the performance limitations of the basic Internet protocol stack, they require either third parties to provide added functionality or applications to replicate content delivery functionality independently of others. As a result, CDN and P2P approaches are insufficient to address the ever-increasing content-oriented usage of the Internet by all its users and applications. Several information-centric networking architectures have been developed to address the limitations of the IP Internet and the efficiencies of using CDNs and P2P applications. These architectures aim to allow all Internet applications and users to obtain content and services by name without requiring a specific system to serve different applications or forcing applications to determine where instances of content and services of interest are located in the Internet. One of the most popular ICN architecture is named data networking. NDN merges name resolution with routing to content and services. Name-based routing and forwarding in NDN have been considered to be necessary to attain an information-centric Internet. It's clear that NDN and other ICN architectures have produced valuable insight in what it means to provide information centricity at Internet scale. However, by requiring a far more complex network layer, using name-based routing to attain an information-centric Internet is only an architectural choice, not a requirement, that has profound implications. It means that efficient content delivery must come at the cost of redesigning the IP routing infrastructure. In addition, servers and clients must also be modified to adopt the APIs needed to use a name-based network layer, and widely successful applications like HTTP must be redone. IDNS and ICN are arguably the first proposed approaches aiming to provide the ICN benefits in the current Internet by leveraging the DNS system. Instead of resolving a URL hostname to an IP address, IDNS resolves content names directly to metadata that contains the address of servers hosting the content, taking into account local caches in the network. However, IDNS does not specify a specific protocol to retrieve content using its method, and instead leave it as part of their future work. ICN also uses the DNS to resolve a content name to a nearby cache or a hosting server, and uses HTTP as the baseline for the transfer protocol. The limitation of this approach are that it is limited to HTTP, requires the connection used in TCP, and which must take place at the application level, causing different types of caching proxy to be used for different applications. The contribution of our paper is to introduce an alternative end-to-end approach to an information-centric internet that we call named data transport. NDT aims to provide NDN benefits without the need to change the internet routing infrastructure or establishing a new overlays on top of it. The main goals of NDT is to allow all internet applications to request content and services by name rather than location. The second goal is to eliminate the performance issues associated with TCP connections, and the third goal is to make an efficient use of a network caching for arbitrary content. The final goal of NDT is to prevent intermediate caches or routers from being able to decode cached content. NDT achieved the previous goals through the integration of three end-to-end architectural components. The first one is a novel transport protocol designed to deliver content reliably to consumers from content servers or transparent caches without the need for end-to-end connections as in TCP. The new protocol is referred to as Named Data Transport Protocol. The second architectural component is a manifest yielding DNS or MyDNS. It is used to provide near replica routing of contents by mapping content names to one or multiple locations where the content is offered. The third architectural component is named data proxies, which are used to provide transparent caching of content at the transport layer while enforcing the privacy of consumers. Content names in NDT are based on DNS domain names, allowing them to be persistent and unique through the hierarchical nature of DNS. With the NDTP help, each content name on the internet is mapped to an individual manifest generated by its producer. A new resource record type, referred to as manifest record, is used to map the manifest of a content object to a list of IP addresses hosting a replica of the content. Each one of these addresses is added to the list as an individual DNS type A record. MyDNS updates this list as needed. This includes sorting the list by the nearest replica based on the consumer's geographical location, issuing the DNS query for the content name. Adding the manifest record to the DNS does not require massive change to the DNS architecture and only require an extension to the authoritative DNS and the local DNS server. This example shows how a consumer is able to resolve a content name to its manifest record and then start retrieving the content without the need for a connection. It starts with an NDTP producer publishing a manifest for a content to its My Authoritative DNS server. When a consumer needs to retrieve a content, it will resolve the content name to its manifest record using the local MyDNS. After the local MyDNS obtains the IP address of the authoritative MyDNS server, it will send a manifest query to it with the content name. Once it receives the manifest record, it will send it to the consumer, where it will start issuing interest immediately to retrieve the content without the need to set up a connection to the server. Applications running over NDT can be cached at the transport layer without the caching logic leaking to the application layer. It works by intercepting NDTP consumers' interests, destined for specific ports or for a specific set of destination IP addresses. For example, we have a client here that sent an interest to the server but got intercepted by a router and redirected to the nearby MP cache. The MP cache surfaces the interest locally if a cache data packet with the same name exists in its content store. Otherwise, add the interest to its PIT table just as an NDN and get the data packet from the server using its IP address. The same interest could be intercepted again by other MP caches on the way to the server. If the MP cache receives another interest with the same name, it will add it to its PIT table to avoid sending duplicate packets to the server. Once it receives the data packet, it will cache it in its content store and use it to satisfy any pending interest. One way to prevent caches from accessing cached content is to use a session-based approach like TLS. However, this will preclude caching by establishing a closed end-to-end connection. Another solution would be to use group keys. For example, an NDTP producer will generate a new key for every new content, and only authorized consumers will have access to this key as part of the manifest. One problem is that members inside the group may know about other members in the same list, simply by observing the chunks names being requested. Another approach would be to encode the data in a way only known to authorized consumers and producers. This is done by combining a content object with all chunks in the content store. However, data encoding alone is not sufficient to provide complete privacy in NDTP. But it could be enforced by using group keys to partially encrypt some of the coded chunks. As a result, consumers retrieving the same content will be requesting different set of chunks. And by using the group key, we are guaranteeing partial caching for all the chunks that are encrypted using the group key. We compared the performance of NDT, TCP, and NDN using our NDT implementation in NS3 and off-the-shelf implementation of TCP and DNS. In this experiment, we compared the total average time taken to retrieve multiple copies of a large data file using NDT, TCP, and NDN. The experiment consists of a source node connecting to a cluster of 6 consumers. All consumers start pulling the content from the source at the same time. Intermediate routers at the edge are configured to forward NDT traffic to MP caches, while routers in NDN can provide caching for any traffic that passes through them. As can be observed from the right figure, all three protocols perform very much the same when only a single consumer is involved. Now, as the number of consumers increases, the completion time in NDT and NDN remain constant. In contrast, the completion time in TCP increases linearly because all the data must be retrieved from the source. This highlights NDT's ability to take advantage of in-network caching as NDN does, but without requiring any changes to the IP routing infrastructure. The second experiment illustrates the inherent benefits of using a receiver-driven, connection-free transport protocol based on manifest. The retransmission and congestion control algorithm in NDTP are receiver-driven but are based on TCP congestion control algorithm. We compared both protocols assuming a scenario consisting of a simple network with a single source and a single sink. The consumer in NDTP issues interest for the content served at the other end after requesting the manifest for this content from the producer. The client in TCP consumes traffic generated by the server after establishing a connection with it using the TCP three-way handshake. The left figure shows the evolution of the congestion window for both protocols, where the growth of the window matches the expected behavior of the additive increase multiplicative decrease algorithm. The retransmission policy in NDTP allows receivers to detect and recover from a packet loss faster than in TCP. This is due to the fact that NDTP does not use connections and apply a fast retransmission strategy enabled by manifest. A consumer in NDTP has a complete picture of which chunks were received correctly and which were lost, and does not rely on partial acts like TCP does. The final experiment highlights how NDT's architectural components work together to provide efficient name-based content delivery over the existing IP internet. We compared the total average time taken to retrieve a large data file in 3 cases, using only transparent caching enabled by NDT proxies. The second one is using redirection to nearest mirroring site based on MyDNS without transparent caching at NDT proxies. The third one is using NDT proxy together with the redirection to nearest mirroring sites based on MyDNS. The left figure shows an abstract view of the topology used in this scenario. In the right figure, we see the average latency incurred in retrieving the content object by a cluster of consumers arriving at random time. The number of consumers in each cluster was increased in each scenario. As seen from the right figure, when only NDT proxies are used, interest from consumers have to reach the producer site, and the benefits of using NDT proxies come from the aggregating interest and caching content. However, because of the short inter-arrival time of interest, only aggregation is useful in this experiment. In our scenario, with 10 consumers, only 10 interests for the same data object traverse the path to the producer. Using MyDNS without NDT proxies results in a shorter retrieval time for consumers, but duplicate packets are sent along the links. When both MyDNS and NDT proxy are used, interest from consumers are routed to the nearest mirroring site and aggregated at the NDT proxies. As expected, NDT performs best when NDT proxy and nearest replica routing through the MyDNS are used. This is because interest from consumers are routed to nearest mirroring site and aggregated at the NDT proxies as well.
In this presentation, we introduced named data transport, the first ICN approach that attains efficient content dissemination without end-to-end connections or modification to the IP routing infrastructure. The design of NDT provides the same benefits of NDN through the integration of a new connectionless reliable transport protocol with name resolution and NDT proxies that support privacy-preserving online caching and native multicasting. To highlight the inherent benefits of the name-based connectionless approach used in NDTP, we implemented congestion and retransmission control algorithms similar to those used in TCP. Far more efficient algorithms can be adapted to be used in NDTP, and this is an area of future work. Similarly, securing the content and manifest records should be viewed as a starting point, and clearly more work is needed in this area. Making native multicast more efficient in NDT is another area of future work.
Okay, thank you, Aziz. So we have a few questions in the Slack. You've been answering them to some extent as they go on, but if I want to sort of summarize, could you sort of capture for us what the real distinguishing characteristics of this approach compared with transparent proxying of HTTP is in the IP world?
Well, the first thing is, can you hear me?
Yep.
The first thing, NDT rely on NDTP, which is a connectionless transport protocol. So NDTP allow us to provide transparent caching at the transport layer, while HTTP applications, caching proxy require like caching logic leak into the application layer. So they only work with HTTP application. While in our case, any application is running over NDTP can actually benefit from the transparent caching at the transport layer.
So if I can sort of follow up, because I think there's still some confusion based on what's in the Slack. What you're saying is that an NDT proxy does not have to understand anything about the application protocol in which the data is encapsulated.
I'm sorry, can you say that one more time?
Transparent blob of some sort?
Can you say that one more time?
In your scheme, the proxies do not have to understand anything about the application protocol encapsulation of the data.
Yes.
Passing through them.
True.
And that's why you say it's independent of HTTP, and you can don't need
so
to
exactly. So all that happened because of the use of manifest to describe the data itself, rather than having a close connection like in TCP, for example. So having the manifest to describe the context of the data allow us to actually provide the caching at the transport layer. For example, the manifest describe how the data is structured into smaller chunks, where each chunk carry a unique name.
So another question is, what led you to restrict yourself to TCP-like congestion control mechanisms?
It's just a starting point. NDT already provide much benefits than TCP-like congestion control protocols. And the first one is because it's a receiver-driven. So the consumer in NDT is have a picture of the whole, chunks that get lost or get dropped in the network. While in TCP-like congestion control protocols, the sender does not have a complete picture and has only to guess which packets were lost and which one were received. Again, far more, better congestion control protocols definitely can be used with NDTP.
Right. So there's a question in the Slack from Ken. Maybe I'll rephrase it a little bit, which is, it seems like since it's named data networking style ICN-like, one of the requirements is the application be sort of request response driven rather than some other interaction paradigm. So Ken mentions things like more symmetric applications that rely on sync rather than request response style applications. I guess they're still pushing on the question about just how application independent the scheme is.
Oh, I see. So I'm not sure exactly what the question is. So what do they mean by sync type capabilities? I'm not familiar with that point.
Well, why don't we why don't you interact on the Slack so that, because I'm not sure we'll settle it live here.
Okay.
So there's a question about scalability of the DNS when you have to store all these manifests. Because DNS data is in theory, fairly small, and the likelihood that you need, multiple exchanges or many packets to get a response. Have you given any thought to that?
Yeah. So we already addressed this in the paper. Any scalability issue can be solved with, a layer of indirection. For example, by using, a separate DNS servers just to handle content records. And HTTP servers already handle, such a load by, hosting the entire directory tree. So in terms of scalability, another or a layer of indirection can solve this issue. there is another issue when it comes to, for example, updating these records. For example, when the producer changes their IP address, and DNS already handled this, for example, by using the scene name in the resource record to map it to an IP address. So whenever the server changes IP address, it's only need to update one resource record, for example.
Okay. So I think we've covered most, at least the first order of detail what's in the Slack. If there are no more questions, we'd like to thank Aziz and our other two speakers in the session. This sort of closes out the technical part of the session of the conference.